We were the super cool, awesome engineers, and we did a Dune buggy. These are the results tables for the roll cage and chassis. The initial design is a welded frame made from alloy steel. My 2 design iterations, I added cross beams to decrease the deformation. For boundary conditions, I had 3 rollers and 1 fixed. Here are the results plots. There are a lot of stress and deformation on the front collision and rollover. However, the passenger and motor loads had minimal stress. If any resonant frequencies are close to the RPM of the motors, it could create stresses. In the closed form solutions, we calculated relative inertia and the theoretical stress and displacements. Here's the results table for the control arm. For the first iteration, a 2-inch plate was added in the middle of the triangle. The second iteration had a 0.2-inch plate at the top right corner of the arm, where the most stress occurs. This is a simply supported boundary condition at the right tubes of all studies. One of the loads was a lateral force of 1200 newtons at the left joint, simulating where the vehicle applies the brakes. The next study simulates landing on 2 wheels. This will cause a force of 3000 newtons from the ground and suspension to be applied on the control arm. Buckling was also tested from the same forces. Here are the results. The final iteration resulted in an overall decrease in stress of 12.2%. The static land test had a 0.3% decrease in stress, and the buckling resulted in factor of safety increasing 10%. This is the modal analysis. The resulting frequencies are cause for concern if the engine redlines around 9,000 RPM. This converts to 150 Hz and might send the control arm into resonance. Here's a table summary of the 3 studies on the rim component. Here are the design iterations chosen. The first iteration is an increase in the center plate thickness from 0.1 to 0.2 inches, which decreased the stress near the bolts. The second iteration is to create 1 mm chamfers for the bolt holes, which would also decrease the stress for that section. The first study is a frontal impact representing the collision. The second study is a lateral impact in and out of the inner frame. The third study is a concentrated impact on the top third of the outer frame. For boundary conditions, the bottom half of holes A and D are fixed, and the bottom half of holes B and C are rollers. For the frontal study, the final iteration decreased the maximum stress and displacement. For the lateral and concentrated study, the final study decreased the maximum stress but increased maximum displacement. Here's the rim's modal analysis with the listed frequencies. The primary concern is when the rotation speed matches the resonant frequency, depending on the deflection. Here we did multiple static analysis on the spoiler. After 2 iterations, the max stress reduced between 12 and 65%, depending on the analysis. These are the design iterations of the spoiler, all using 6061 aluminum alloy. The hole sizes in the legs were reduced 35% after the first iteration. In the second iteration, a 1.5 fillet was added to reduce stress concentrations. The 3 load cases studies were downforce, inertial turning force, and inertial stopping force. These loads were calculated using a vehicle speed of 45 meters per second. These are the study results with images from the base design. Reducing the hole size and adding the fillet resulted in the greatest improvement, reducing max stress by 32% and displacement by 64%. Here's the spoiler's modal analysis with the resulting frequencies listed. The low frequencies are a concern for an engine idling at 600 to 1000 RPM, as it might send the spoiler into resonance. This is an SN curve for 6061 alloy. Using the calculated cycles of a 5-year lifespan and the max stress from the inertial turning analysis, the data shows that the part will not fill after 5 years. Here are the results for the brake disc. Here's the design iterations for the brake rotor disc. The major difference for the iterations had the 5 large holes of the initial design filled in. The first iteration filled in all the other holes besides the rear axle and 5 bolts, while the second iteration had a lot of smaller converging holes. The disc is fully fixed around the rear axle. We did a torque load to simulate braking while the vehicle is moving forward, and a thermal study to simulate the heat the disc experiences from interacting with the brake disc. Lastly, the weight of the buggy on the top half of the rotor disc. Here are the results from SolidWorks. The other iterations were better at handling the weight stress. The first iteration was better at handling the stress from the torque compared to the second iteration. The other iterations were better at handling temperature than the initial iteration. This is my modal summary. The main worry is that the resonance could reduce the longevity of the brakes. Our biggest concerns for failure for this vehicle are large impacts like crashes and jumps, environmental corrosion, and lack of maintenance. Thanks for listening.